A very good afternoon to all of you. And uh, in continuing down the previous two uh, lectures that I delivered on the philosophy of physics, uh, here I would like to move on in continuation with where we stopped last time. And uh, actually, we were in the domain of, we started from classical mechanics, talked about some basic fundamental phenomenon that could be explained uh, uh, in the Newtonian world. And Newtonian world is a classical world, and everything in Newtonian world is completely deterministic. You can determine the future of an action if you know exactly the initial state of that process. And then we moved on and talked about some of the basic phenomenon that could not be exclusively uh, defined or exclusively presented by classical theory of physics. And some of the examples that we already have discussed are like uh, the problem of the problem of quantization, the problem of hydrogen atom, photoelectric effect, Planck's black body radiation law. Uh, uh, there were a range of problems that could not be explained classically. And if I would have to add something to that, if we take an example of radioactivity, we got to have some elements in the periodic table which are unstable, and their instability leads to the emission of some particles like alpha particles, beta particles, and gamma particles. And when we treat the problem of alpha decay, when we try to understand the problem of alpha decay in the context of classical physics, the classical physics it exclusively fails to explain the process of alpha decay, and what alpha decay is, that alpha particle that's emitted by a radioactive nucleus. When we measure the energy of this alpha particle, it nearly comes out to be of the order of few megaelectron volts. If I have to be precise, on averages, it's nearly 4 megaelectron volts. But the potential barrier that's offered by the nucleus to this alpha particle is extremely large. That potential barrier may certainly vary, but on an average, its value is 24 to 26 megaelectron volts. So practically it's impossible, classically it is impossible for this alpha particle to cross that barrier, because the barrier is too high and the energy of this alpha particle is extremely small. If that's the case, then classical physics has no answer to this problem. And this problem can be resolved using the principles of quantum mechanics. So here I would like to figure out some of the important things. Is that what we have is we have quantum mechanics, which to a very good reasons, to a very good accuracy, can predict the atomic and molecular systems. And this theory was extensively developed by a range of people, and there were key players in quantum mechanics. It was Max Planck, it was Niels Bohr, it was Erwin Schrödinger, De Broglie. They were the key players. Even Einstein had its role in terms of photoelectric effect. But when we go to the formalism of quantum mechanics, we find some of the objections from Einstein's perspective, especially in the context of what we call as entanglement between the two particles, what Einstein calls as the spooky action. I mean, you can actually, if you're trying to measure the state, if you have some kind of weird situation where you have two particles, they interact with each other, and after their interaction, if you take the two particles away from each other and making an action on particle 1 will instantaneously translate an action to the particle 2. So in that domain, Einstein was he was not comfortable with the overall formalism of quantum mechanics. And there is another part that's what we call as a special theory of relativity, and this special theory of relativity later on is boiled down by Albert Einstein to what's called as general theory of relativity. Because if we go back to the Newtonian domain, in Newtonian world we have a three-dimensional space, and we have time, and time is absolute. And what that means is that if I bring say two clocks, and these two clocks are synchronized, I mean the time that you can measure on clock 1 is exactly same as that of the time that you can measure on clock 2. Now, if you take these clocks anywhere in the universe, and they will maybe a clock that you will allow to stay on the planet, and the other clock you will take it on a tour anywhere in the universe, and when the clock will come back, they will exactly have the synchronization. The time that you can measure from the clock that's on the planet will be same as that of the time that you'll be able to measure on the clock that has moved into the universe. And this is the reality of the Newtonian mechanics. So all synchronized clocks, whether you move them or whatever you do with these clocks, you take them to any corner of the Newtonian universe, they are going to give you the same kind of time. So time is of course a dimension in the Newtonian mechanics, but it's an absolute entity. It's going to be same for any kind of observer, any kind of measurement that you will make on these clocks. They are not going to change at any level. But Albert Einstein comes up with the two important postulates, and the first postulate says that the laws of physics are same in all inertial frame of references, and the next important postulate is that what he does basically, he puts a limit. He puts the limit to the speed of light, which is not the case in case of the Newtonian physics. In Newtonian physics, you can have a particle that can move in this space, and it can attain any kind of velocity. It can attain any number of velocity as long as you're able to provide that kind of energy to this particle. And what seems to be different here in the Newtonian in Einstein's model is that what Einstein does is that he puts the limit to the speed of the particles. And what does this? How can we explore this limit? First of all, the limit. If I take an example of suppose I have to move from planet Earth to some other planet on some other galaxy, and maybe that galaxy is at say for example 100 light years away from this galaxy. So I'm in galaxy A, and there is an event going on in galaxy B, and between the two planets there is a separation of say 100 light years. Now, if I drag on the Newtonian physics in this problem, and suppose a party is going on that galaxy, on the galaxy B, where we have planet 2, and we have to reach that planet, say, in a period of 1 month. And Newtonian mechanics does not provide any restriction. All you have to do, you must have all kinds of things that are essential for you to have a rocket ship that can move from galaxy A to galaxy B. All you have to do is to provide also those provisions by virtue of which this rocket can attain all possible speeds, and you can reach out to galaxy 2 under all circumstances, provided you provide all that framework to the rocket ship. But if we treat the same problem in the domain of in the domain of Einstein's world, Einstein's universe, since Einstein puts a limit to the speed of light, it means that you cannot have any material particle that can move faster than that of speed of light. So if that's the case, and talking about these two planets, one existing in a galaxy A, another existing in galaxy B, and between the two galaxies there is a separation of 100 light years, it's never going to reach in that framework of time. It's not going to reach on the planet B in the galaxy, on the planet 2, which is in the galaxy B, because there is a limit that is imposed by special theory of relativity to the speed of the spacecraft. So if your spacecraft will be utilized to go to another galaxy, it certainly will have to go with the speed less than that of the speed of light. So preferably it will not be possible for the spacecraft, it will not be possible for us to have a party on that planet which is existing somewhere on galaxy B at a planet which I have numbered as planet 2. So here we have a constraint to the speed of light, and as I talked about the time, as I talked about the time, in Newtonian world, in Newtonian universe, time is an absolute physical quantity. If time is a physical quantity, you can have all these clocks. These clocks will give you the same measure of the time, then all the clocks will return back to the planet. But if you perform the same experiment in the what time dilation tells us, that there is a difference. There's a difference of the time that's measured by the body which is moving at the relativistic speeds, and an observer who's measuring the time of that object that's moving in the space. And what we obtain using the postulates of special theory of relativity is we obtain the time dilation. And time dilation is exactly, it's telling us that time is not absolute. So time, it has a different meaning for different persons. It has a different meaning when it comes to a person moving with the speed close to the speed of light. And it has a difference when you have a person in one domain of speeds, another person in another domain of speeds, another person in another domain of speeds. The three persons are going to experience the different states of time, what we call as light cone in special theory of relativity. Every individual has its own light cone. So what does it mean? It means the thing that I was talking about, those clocks having some range of clocks synchronized, and when we have synchronized the clocks, if we send the clocks throughout the universe with different speeds, and all of these speeds are somehow comparable with the speed of light, what we are going to measure is is that different clocks will give us the different measure of the time. So time is not an absolute physical quantity. Time is a relativistic quantity. It certainly depends on, it has a dependence on the speed with which the object is moving. Even though if the speed is less, then this time dilation may not be that much visible, but it's rightly said that whenever you move from London to United States of America, there has to have some minute correction that you have to carry to your mechanical watch that you are carrying with you. So time dilation is a reality, and it has been experimentally confirmed. And the next thing here is that the dimensions of an object, I mean, what we call as length contraction, when we use those postulates of special theory of relativity, they lead us to another equation in terms of the length of an object. And what we see is that the length of an object is not an absolute physical quantity. It is a relativistic quantity, and it certainly has the dependence on the speed with which the rod is moving. So if you have something, some kind of a spaceship, and this spaceship is moving in space, and if we measure its length and its speeds are somehow increasing at every interval of time, and that increase in the speed of these machines, these rods, when we measure their length while they are in motion, their lengths seem to be shortened. Their lengths are measured to be shortened, and if I quote down this kind of an example, if you have some rod like this, if you take down this rod to these speeds, the speed close to the speed of light, we are measuring a shorter length for the rod every time we're making measurement when this rod is acquiring that state of speed. And the next important thing is what we call as the twin paradox. And I remember when I used to be in graduate schools, we used to have a story when we used to talk about the twin paradox. And I don't know whether the story about Albert Einstein is true. I have no idea about that, but somehow we used to exchange that story whenever we used to talk about twin paradox. And the story was like this, that there happened to have a time when Albert Einstein was delivering a lecture in some kind of auditorium, and he was talking about special theory of relativity, and he was coming up with all those equations, the equations of special theory of relativity, articulating down the equation, the time dilation, length contraction, talking about the postulates of special theory of relativity. And there happened to have a journalist, a young lady journalist, and she comes and when the lecture that's given by Albert Einstein, when this lecture is completed, and the question and answer session starts, a lady who happened to be a journalist, she stands up and she tells Albert Einstein, okay, come on, I don't understand all the mathematics that you have been showing us on the screen, but I am a journalist, I have never gone through mathematics. How will you explain me something like twin paradox? And it is said that the reaction of Albert Einstein was, and what he said to this young journalist, he told her, come on, okay, let me do one thing, let there be Albert Einstein and the journalist, and let the journalist send Albert Einstein, who happened to be of the age of say 55 years old, and the lady happens to be extremely young. And what Einstein tells her is that, come on, you put me into a spaceship and take this send me into the space and make sure that the spaceship goes with some speed which is close to that of the speed of the light, and and maybe you will have lived some time on this planet. Maybe you have lived 20 years on this planet, and I'll be in the space, and when I'll come back, I'll marry you. That means I'll not be aged when you will send me in that spaceship, but here on this planet you'll be aged, and maybe our ages will be comparable at that time, so that we can have a marriage. I mean, this is how we used to exchange the story of Albert Einstein. I again tell you, I don't know whether this story is absolutely true or not, but the argument of the story is same. The twin paradox has the same thing to tell us, and what it tells us is that that if you have twins, they're born at the same time. That means on the planet Earth, their ages are same. They are the two synchronized clocks. Their ages are same. But if somehow you manage to send the brother of the twins into the space, put him into the space so that the brother goes into the space and moves with the speed close that of the speed of light in a spaceship, and after a good amount of time, the brother comes back from the space. When he comes back from the space, the one who is on the earth, he will be old enough, and the one that was being sent into the space, he will be young enough. So this is what leads to what's called as twin paradox. So I think this till now, what I talked about, I hope you will enjoy the things that I have tried to share with you. So I'll stop here, and we'll proceed in the next lecture in the same domain, where I'll try to take the philosophical arguments of special theory of relativity into the general theory of relativity. Bye.